Good morning. We'll be starting today with chapter 14, and we'll go through um, it, and then we'll talk a little bit about some of the updates that have to do with the Siemens, their use of object-oriented programming. So we're down at chapter 14 today under hybrid text. We'll pull it up, and we're going to start it through. First of all, this chapter is about an example that I want you to run through and do. That's the first thing I want you to do, is to do this example, because it's important that we understand in a practical way how to write an object-oriented program and what the implications of it are. My personal experiences have always been toward not doing encapsulated programming, because everything that I did pretty much was a one-time deal. But I understand the advantages of using it, and there have been times when I would have liked to have used it, but not many. So I want you to understand that while this is an important concept, it's a concept that that we can take parts and pieces from and maybe use it wholeheartedly. I think in some cases that the Siemens people use it a lot, and maybe if you inherit a program from somebody from Germany, you will have to do some work with the concepts that are talked about in this chapter. The concepts are very powerful, and I'm not trying to say that it's the best or anything like that. I'm just saying this is something that you should know something about. Everybody's talked about over the years top-down programming or structured programming, and always when I'm in a situation where people have tried to define what they want to see from the written programs, they always say no spaghetti code. Well, that's hard to define. It's easy if you are looking at it from the backside sometimes to say that sure is spaghetti code. But I think most of us want to say that no, we don't write with spaghetti code, but it's harder to say exactly how we do write it sometimes. So I've always tried to picture the idea of OOP, or object-oriented programming, with the idea of Legos. And as you put them together, they form a whole, but they're each individual separate modules. And that maybe is a gross exaggeration, but if you can look at the idea of a Lego and how Legos are put together to make some kind of a form or something, that gives you an idea of what we're talking about. And hopefully it will encourage you at least. There's a program at the end of this chapter that you can do that will enforce your idea of object-oriented programming, and we'll discuss that in a little bit. Siemens has two basic types. One is called a function and one is called a function block. And in no way am I trying to minimize the way that I've written this out, or that I do have at the end of this chapter a rather extensive cut from the Siemens, one of their more recent updated books on this subject, and I go into it a little bit more there. So if you're sort of put off by the way that I've done it, you can look at their pictures and their way that they've done it, and you can see how they've explained it. And Alan Bradley, through their RS Logic 5000, have introduced a device called an AOI, or add-on instruction. And while we'll not feature it in this chapter, it is similar to a function or function block. And the only problem that I would say with the AOI is be careful if you're having programs that have interrupts in them, because AOIs are susceptible to changing of data in an interrupt. Now you say, well, wouldn't the same happen with Siemens? Well, they've got ways of blocking that. And while I'm not going to go into the depths of it, they do block that pretty much, so that you're protected from an interrupt. If an interrupt happens, the function block or the function should come back with the same data that it had originally and not being changed. So arguments for the benefits of reusability include reliability. Now, that is a biggie. So if you change it once, you change it for all. That's something that if you have a number of occurrences of something happening, you only want to have to make a change in one spot, and that affect all of the occurrences. Efficiency of programming effort. Again, like I said before, most of the time that I've done programming, this does not apply, but you could have it possibly apply. Saving of time in the programming development. Again, I think you have to spend a little bit extra, but maybe you get something from it if you do have those recurring issues. This idea of maintenance, it can be of use, although at times, if you have too many things calling other things, calling other things, calling other things, the eyeballs of a maintenance person kind of glaze over. So you have to be careful. And consistency of programming, if you are doing the same thing again and again and again, this is probably something you want to consider. Some additional terms called encapsulation, inheritance, and polymorphism. These are computer terms, and I'll let you go through these and read these. The encapsulation basically means combining up programs and data to manipulate an outcome in an object. Inheritance means building a hierarchy of objects, each with inheritance. Polymorphism, allowing one set of actions to share it with an object with another set of actions. Now, with Siemens, there's two basic types. One is called a function, one is called a function block. In this chapter, we're talking about the example at the end of the chapter is a function, not a function block. We've already talked about data blocks already. When we were talking about setting up an array, you had to do a data block. And we've already talked about organizational blocks from chapter 3 on when we had OB1. So OB1 was that cyclical program that was in the background, always running. It was not a timed program. It was when something else wasn't running, we had good old OB1 going back there and just churning along. So we talked about OB1. There are other OBs, and we'll talk about some of those as we go through the rest of the book. We'll create some OBs that are cyclical, that are timed interrupt, cyclical interrupt programs that come in on a clock and execute, and then are done. So when they are done, they're off, and then OB1 comes back and runs for a little while. So again, OB1 is not a timed interrupt or not timed program, but it does carry the ball for most of the time. Functions are with basically standalone, and they have the ability to do a specific action. Function blocks depend on a set of data from a data block or multiple data blocks, and that gives us the idea of the ability to write programs that have either one set of data or multiple sets of data, and you can, in these data blocks, you can create all kinds of sharing of information. Either, well, that's at the end of the chapter 2. Then in the Siemens or the Siemens cut sheets, we're going to talk a little bit more about that. So we've got functions, function blocks, and object blocks, and those are the three places where we can execute programs. And these are standardized for IEC 61131, so you can look at that IEC standard, and you can see these three and see how they're called. And this is a standard idea that supposedly is between multiple manufacturers. Now, in these, you have things that come in, things that go out, and the things that are called in-outs. And we'll talk a little bit more about each of these. I think it's easy to see what something is that's coming into a function or function block, something that's going out from a function or function block. But the in-outs are a little bit more tricky, and we'll talk a little bit more about those as we go along. Temporary are variables that are just in that particular block, and they exist in that block, and that's the only place they exist. And so we have temporaries as well. And then we can also have data that we can share outside of that block, which would be in a data block. Okay, so the idea of data blocks. This is a picture, early picture from Siemens, types of blocks, and an OB, object block, calls other blocks. This is a programming block. OB100, we haven't really talked about that before, but that is the block that starts up. It only runs one time. It runs when you first go from off to run, or from when the green light turns on. So when the green light turns on, OB100 is the first thing that occurs, and then it goes away and doesn't happen again. So this is a setting up, a startup, a setup of your data and that type of thing. And it's only run at startup. Other blocks can come in. There are timed blocks, either on interrupts, hardware interrupts, or on a timer. Hardware interrupts. And there's also diagnostics interrupts, and some of these are defined. OB82, timing error is OB80, so some of these are dedicated blocks that you can't use. They are already dedicated. So now we're going to go back and we're going to talk about our problem that we had in chapter 8, and we're going to revisit that program, and we're going to say, instead of having to type all that stuff all those times, let's just create a function and do that ourselves. So if you remember that example, there were two words, and we were going to add the second word to the first word, and in this case we're just going to use a byte. But if you do that, you can actually bit by bit by bit build an adder. And also we had the ability to take the 2's complement of this, so you could actually say we're subtracting. So that's what we're going to do. Now, how do you do that? Well, click on the block over on the left and say add a new block. And in this case, we're going to click on a function. Click on this green one right here. And then we're going to come up here and we're going to start writing a program. Now in this little spot right here, there is an area for variables, and you can define them. In, out, and in, out, temp, constant, and return type variables. We're going to concentrate on ins and outs and outs. Now these contacts that we're going to have are all contacts and coils. They're bools, in other words, and we're going to call them by a name internally. It's a generic name. It doesn't say bit 0, bit 1, bit 2, bit 3, bit 4, but it's just a bit. And we're going to type those in. And you notice that the in out uses the carry bit because it both comes in and it goes out, because it's affected both ways. So as we're doing this, we notice that we're typing these in a logical format, just like we did before. But once we have this done, we don't have to type this again. It's going to be a block that we can use in our other program, and we just call it, and this will do that addition for us. Notice there's a pound sign in front of these. These are these internal bits. You don't have to put the pound sign in there. It's provided for you, but inside this program they show up. So this is the typing of the program to put it in there. And okay, so this is the addition block then. And notice what we have. Now, after you've done this, you have to compile it. So you can't get this to work until you've compiled it. But once you've compiled it, then you can call it up. Now watch what happens in OB1. This is the program in OB1. So here we have word 1 and word 2, And notice that we have .x0, .x0. So we're handling bit 0 separately because we don't need a full adder, we just need a half adder. So we just did that separately. But now this is that function that we just typed in and compiled. And here is the function for bit 1. See how we address this? See, here's our internal bit, here's our internal name, and here's our actual name that we're using to execute the program. All right, so these are the internals, the function names, internal. These are our internals. This is the in out, and this is our out bit. So here we go. We put this in, and now we can call this 15 times, or excuse me, for 8 bits, you can call it 7 times. But you call this block 7 times, and the next time it would be with word1.x2, word2.x2. And you say, well, couldn't I have all of them in one block? Yes, you could. You have like a spider web over here on the left. You have like a spider web over here on the right, but you could do that. If you wanted to pack them all in, you could. No reason to, but you could. So some people have functions with a lot of inputs over here and a lot of outputs over here, but we want to keep it simple. So we're going to do this. We're going to call this 7 times for a byte. This would be bit 0, bit 1 through bit 7 would be called over here. Okay. So we come down here to storage of variables, and we have static variables. And this is something that's very important because function blocks, FBs, use static data internally. So if you're wanting to write large programs and you want to have variables and you don't want to have to use your M table for them, what would be a logical place to write those programs? Well, it'd be in an FB. And in the FB, then you would have these static variables that are assigned by name, and then they can either be for just that program or they can be accessed by other programs as well. So you can have static local data or you can have global data as well. So either way, you can have static local data or global data. But this gives you an idea that with FBs, function blocks, and static data, that you can write large programs, not having to worry about the M table, but static variables that are defined in that function block itself. So this gives you a little bit of an idea of the calling of functions. And OB1 could call something, and then that can call something, and it can be brought back. Call something else, and that can be brought back, and then that can be reported back to here. So you get an idea how functions or function blocks can do this, one calling the other and then coming back with data. Okay. So don't forget this idea of temporary local data and static local data. Static local data is useful just like if you're writing with an Allen Bradley program. You could write the same exact program in Siemens with a function block and static data. And it looks exactly the same. No M table at all. It's just all right there. It's something to think about as you're creating programs. So creating a programs in function blocks probably is a very good way to go. So can I have a function block with more than one set of data? And the answer is yes. You can have a single instance block, or you can have a multi-instance block. So here is a function block, and you can have a block with single instance or multi-instance, and that gets a little bit more than I want. Okay, so we're back with the problems we have here, and this one asks for a Okay, so we're back with this question here. It says, in OB1, there's a function, FC1, that accesses the following, and it's has a bit called innum, an in bit, and then outnum, and then if you look at the 16 bits in innum, all 16 bits get passed along to outnum except for bit 0. This is a function you could possibly even use to write, but bit 0 is the OR of this bit or this bit. So exclusive OR, excuse me, of bit 0 and the variable bit 0. So you can do this if you look at it by looking at each individual bit. You just carry it through. So you would have each individual bit going to a specific output. So innum is innum. So innum dot x15 would go to outnum dot x15, and that carries that bit right through. Same way with bit 14, bit 13. So you just do dot 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 down through bit 1, and then bit 0 is an exclusive OR. So you could say, okay, so innum dot x0 and not in bit or not of innum and then normally open of in bit. Give me my out bit num dot x0. So it's a little sloppy, but it does show you the logic. So you have 15, 14, 13, 12 down to bit 1 of like this. Bit 0 would be like this. Are you done? No, you also need to put in a table. So you have a table of ins and outs and in outs. What are the ins? Well, the ins are in num and in bit. The outs are out num. And you got it. So this is a table of the inputs and the outputs. This is the logic that you would use, and then you would compile this, and then you would have a function like this that you could use in your regular program. But the idea of this is a good question that I could ask you on a test that shows whether or not you understand the idea of a function or not. So these are good test questions. That's what it boils down to. Here's another one. In problem number 11, here we have the same thing, only it's we're anding the last 8. So you would do, this one would be in num dot x15, and it would just carry through to out num dot x15. You do dot 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 down to bit 7. Bit 7 would be anding of in num dot x7 with in byte dot x7. That would give me out num dot x7. Dot 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 dot. Done. Now, are you done? No, you need a table. And in that table, you have the word innum, inputs, innum, in byte, and outs, you would have outnum. And in outs, a blank. That gives you an idea. We're going to go through and do a couple more of them as well, but that gives you a little bit of an idea. Okay, number 12 is a little bit more difficult because this one has a little bit more logic in it. So here we have two words that are competing for the output, and basically at that point in time you have a switching that how many bits from in num1. So if you have this, you would have to say something like if so bit num if it's less than 1 or less than whatever, if it was less than 1, then you would do greater than equal. Back with appendices, and we're going to kind of go through this first appendices really quickly. But the second appendix is really from a text that Siemens has that goes through some of this ideas, and we're going to skip some of this, but we're going to talk about some of it rather detailed. So from version 14 on, they changed some of the things that they did, and so we are going to go through and going to talk about some of this this is just their material, and I'm going to talk about it. This is called the different types of instances, and so it talks about input, in, out, and then static. Some of this is stuff that we've kind of talked about before. Multi-instanced function blocks. And I'm not going to go through a lot of this in depth, but I wanted to show it to you because it is important that you know that where this exists, and that there is some of this stuff that you can do. Okay, so sometimes you want to wonder how to get data from one place to another for transferring of in-out parameters, and this talking about in-out parameters. And there's a parameter instance. I'm going to get into details with this one, but you might want to review it. And global data blocks. Talks about global data blocks. Available to the entire user program. So global data blocks are central data memory blocks, and you can use them from anywhere. High-speed access. So sometimes you want to be able to save data and be able to bring it back, and this talks about how to do that without having to change the controller to a stop state. So you can review this on your own. You will need this. And down the road, you will need this. Not necessarily in this class, but you'll need this ability. Okay. Shows you how it's done. Reusability of blocks. Again, that's one of the advantages of blocks. You can reuse them for again and again and again. I don't understand necessarily about the numbering of blocks, but they are automatically assigned by number. So you can see these numbers of blocks. So these blocks appear over on the left-hand side right here, and you'll see them. You'll see that. So they appear on the left-hand side. Again, this is two different ways of putting in variables. You can put a number in there, a variable number that you can actually change, or that really this is a fixed one, not a variable. Or you can put it in by variable name, by reference, and you can then change this one. It talks about different ways you can do the functions and function blocks. Memory concept. Global memory is available to each block in the user program. Local is only available in that block. If possible, only use local tags. Yes, you can use the blocks universally in a modular fashion. This is something you're probably going to review many times before you get this down well. Okay, a couple more things and we'll be done. Access speed. Various areas, various types can be faster or slower. So you want to be in the green or the fastest. You do not want to be in the red. So review where this is quick. That would be the best place to be. Retentivity, big word, but in case of a power failure, you want your variables to come back. So you want to have them so that they're retainable, and retentive data maintains its value when the controller goes to stop and back to run, or in the event of a power failure and restart of a controller. You want that. Most of the time, you want that. You want your program to reset to a logical position, but you want your data to be in its last state most of the time. And you can set the data as to retentive, non-retentive, and in function blocks. You can set it that way. And that's how it's done. Static variables, retentive, non-retentive, start value.